Hi guys. In the last video, we finished as this slide. We can explain the IR chart, and we discussed about many function groups. And today, I would like to complete this discussion. And let's start it. Today, we would like to talk about many families in organic chemistry. So, first of all, the alkanes family, and this is a combination of C single C and C single bonds. So you can see octane 10 8 carbon atoms. So you can see C single C stretches and bends around 1030 160 to 1470 centimeter minus one. So when you focus on the structures, you can see many single bonds. So the single bond between CH2 and CH2 bond is around 1450 to 1470 centimeter minus one. And the bond between methylene and methyl group bond is around 1360 to 1390 centimeter minus one. And also you can see sp3CH between 2800 to 3000 centimeter minus one. So as you can see in this chart, we have three different peaks exactly stretch and bending. And at the left side around 3000, you can see the sp3CH. And in the right side, you can see two different modes and two different signals. Actually, CH2 bond CH2 and CH2 bond CH3. So we can discuss about the second family. It's called alkenes. And the addition of C double bond C and vinyl CH bonds, you can see double bond C stretch at 1620 to 1680 centimeter minus one is a weaker as substitution increases. So we can discuss or explain the octene, one octene. You can see vinyl CH stretch occurs at around 3000 to 3100. And the difference between alkane and alkene or alkyne CH is important. If the band is slightly above 3000, it is vinyl SCP2CH or alkynyl SCP-CH. If it's below, it is alkyl SCP3CH. So from here, in this region, you can determine which bond, which is bond, which is CH bond. If you can see here below 3000, you can determine this is a CHSP3. So above 3000, you can see CSP2 vinyl CH. Above vinyl CP2 CH, you can determine and identify the CH alkyne. So the third family is alkynes, and the addition of C double bond C and vinyl CH bonds. So you can see here one octane, and C double bond C stretch is around 2100 to 2260 centimeter minus one, and the strength depends on asymmetry of bond, strongest for terminal alkene and weakest for symmetrical internal alkenes. So the CH of four terminal alkynes occurs at 3200 to 3300 centimeter minus one. And the internal alkynes are C triple bond CR would not have this band. So from this chart, you can identify two different signals IR. From the left side, you can determine that this is CH alkyne, and from here, around 2200, you can identify C triple bond C. And we can also discuss the aromatics, and we have an example, ethyl benzene. and due to the delocalization of electrons in the ring, C single bond order is 1.5. The stretching frequency for these bonds is slightly lower in energy than normal C double bond C. So these show up as a pair of sharp bands. It's around actually 1,500 to 1,600. Lower frequency band is stronger. CC single H bonds of the ring show up similar to vinyl CH at 3,000 to 3,100. So if you focus on the structures, you have two different signals for IR. You have a CH aromatic, C single C, and C single H. From here, you can identify the C single H around 3,000, and from here, you can identify CH aromatics. So if the region between 1,667 to 2,000 centimeter minus 1 is a free of interference, such as C double bond O stretching frequency is in this region. A weak grouping of peak is observed for aromatic systems. Analysis of this region called the overtone of bending region can lead to determination of the substitution pattern of the aromatic ring. This region is really important. From here, you can identify monosubstituted or dia, ortho, or meta position, one to die substituted meta positions, or you can identify also para position, one for that substituted. So from here, as you can see, you have had four different shapes. If you focus on four different shapes, you can determine whether the structure is mono substituted, ortho, meta, or para. So let's discuss about insecurity systems. The substitution of aromatics and alkenes can also be discovered through the out of plane bending vibration region. However, other peaks often are appear in this region. These peaks should only be used for reinforcement of what is known for hypothesizing as two function patterns. So you have four different numbers. If you know about these numbers and focus on it, you can determine the different signals around the structures. You can identify function groups. You can identify the alkenes, whether they have monosubstituted or transsubstituted, maybe can be cis or vinyl allyl. Okay. And from here also in the right side, we can determine whether the structure in the aromatics mono or meta or sodia or para. From here, you can determine the structures, we can determine the function groups, the structures. This can help you a lot in determinations of final structures, also with the help of NMR spectroscopy. Let's discuss about ethers and the ether addition of C single O single C, asymmetric band, and vinyl CH bonds. As a good example, like isopropyl ether and short strong band for anti-symmetric C single O single C, stretch at 1050 on to 1150 centimeter minus 1. Otherwise dominated by the hydrocarbon component of the rest of the molecule. So from here, the red shadow, you can determine from here the function group C single O single C. This is really important to identify the structures with the help of the NMR spectroscopy. Let's discuss a very important families, alcohols. And from here we have an example, 1-butanol, and you can show many signals, but the most important signals is OH. The strong crude OH stretch from 3,200 to 3,400 centimeter minus 1. Like ethers, you can have The structures have also C single O stretch from 1050 to 1260 centimeters one. A band position changes depending on the alcohols. Maybe it can be primary alcohol, so we can show signals like 1075 to 1000, and secondary alcohol 1075 to 1150, tertiary alcohol 1100 to 1200, and phenols 101,080 to 1260. So as if you show the IR chart, you can identify very important signals. From here, you can identify the broad signals OH. So she takes this shape like a waves, and in the right side, from here, you can determine C single O. Let's talk about amines, and we have an prime and an imaging example, 2-aminopentane, and shows that NH stretch for NH2 as a doublet between 3200 to 3500 centimeter minus 1, symmetric as anti-symmetric modes. NH2 has deformation band from 1590 to 1650 centimeter minus 1. Additionally, there is a wake band at 780 to 820 centimeters one. This is a diagnostic. So if you see this chart, you can identify very important signals from here around 3300. And it talks about two spikes, actually, two spikes. And if you saw two spikes, so you have NH2. If you have one spike here, you have an H. And the other signals is W is about NC single bond. Let's talk about amines, and NH band for R2 NH occurs at 3200 to 3500 centimeters long as a single sharp peak weaker than OH. Tertiary amines have no NH bond, so will not have a band in this region. And a good example is pyrrolidine, and you can see here around 3200 to 3400, one spike, one single sharp peak, and identify NH peak. So as a review, then expect the bonds to each region to 2700 to 4000 centimeters one. Peaks from 2085 to 3000 are simply sp3ch. It's the most organic molecules actually. Above 3000 is learned sharps, not wave numbers. So from the shape of the signal, you can identify the functioning group. Very important functioning group actually. If you have a broad U-shaped peak, so the structure is contained OH bond. If you have a sharp one spike is so C triple bond CCH bond. If you have V-shaped peak NH bond for secondary amine actually R2 NH. If you have W-shaped peak, so NH bond for primary amine R NH2. If the structures have small peaks shouldered just above 3000 centimeters one, so this is C double bond CH or phenyl H. So we can talk about aldehydes, and we have an example cyclohexyl carboxylaldehyde and C double bond O carbonyl stretch from 1720 to 1740, and that is very sensitive to conjugation, as are all carbonyls upcoming slide. A highly unique sp2ch stretch appears as a doublet 2720 to 2820, something called Primi doublet. So here in the right side as a yellow, you can identify the carbonyl group, and from here around 2500 to 2800, you can identify the CH aldehyde. Let's talk about ketones, and we have an example 3-methyl-2-butanone, a simplest or of the carbonyl compound as far as IR spectrum carbonyls only, and C double bond O stretch occurs at 1705 to 1725 centimeter minus 1. And from here, as this is a yellow shadow, is identify the carbonyl fractional group. So we have a talk about esters, and esters like ethyl bivalate, and here you can identify C double bond O stretch at 1735 to 1750 centimeter minus 1, and you have a stronger bond for CO as a higher frequency than ethers or alcohols at 1150 to 1250 centimeter minus 1. So if you see this chart, you have two different signals. The yellow is about carbonyls and the red is about C single O. Carboxylic acid is really specialized in IR. You can identify easy the carboxylic acid in IR. And we have an example for phenylbutyric acid and give you the message of their spectra. C double bond O bond occurs between 1700 to 1725 centimeter minus 1. The highly dissociated OH bond has a broad band from 2400 to 3500 centimeters when covering up the half IR spectrum is in some cases. If you see this chart from here as the left side of this chart, you can see the long distance signal. This signal is really special for OH carboxylic acid. If you have this shape, you can identify easily the carboxylic acid in the structures. Also, around 1700, you can identify the carbonyl group of carboxylic acid, and around 1200 to 1400, you can identify a C single C or C single O. Acid anhydride, and we have an example propionic anhydride. Coupling of the anhydride through the ether oxygen splits the carbonyl band into two with a separation of 70 centimeter minus 1. Bands are at 1740 to 1770 and 1810 to 1840. Mixed mode C single O stretch at around 1000 to 1100. If you have acid anhydride and see this shape around 1800, you have two carbonyl signals. If you have this shape, you have an acid anhydride functional group. Let's see acid halides and an example propionyl chloride and cleavage band at 1770 to 1820 for carbonyl group. Bonds to halogen due to their size occur at low frequencies. Only Cl is light enough to have a band on IR. The CCl is at 600 to 800 centimeter minus 1. So if you focus on that IR chart and focus on around 1800 and focus on this shape actually, so you have an acid anhydride halides, and the red area describes that the presence of halogen actually. And we will talk about amides, and we have an example with amides and display features of amines and carbonyl compound. You can see C double bond O stretch at 1640 to 1680. If the amide is primary, NH2, the NH stretch occurs from 3200 to 3500 as a doublet. So if the amide is secondary, the NH stretch occurs around 3200 to 3500 as a sharp singlet. So from this example, we have NH2, so do we have two hydrogen. And if you focus on the IR chart, around 3400, we have two spikes actually, two spikes for NH2, and around 1800 you can see the carbonyl group actually. Let's see and discuss the nitric group. Proper slowest structures give a bond order of 1.5 from nitrogen to each oxygen. Two bands are seen, symmetric and asymmetric, at 1300 to 1380 and 1500 to 1570. This group is a strong resonance withdrawing group and itself is vulnerable to resonance effect. So from here, if you have two signal, and this two signal as described in the yellow shape in the IR chart, so we have a nitro group. So let's discuss nitriles and the CN or C triple bond N group. As example, propionyl nitrile. Principal group is a carbon-nitrogen triple bond at 2100 to 2280. This peak is usually much more intense than that of the alkyne due to the electronegativity difference between carbon and nitrogen. So if you have this signal and the signal is above 2200, so this signal describes the presence of C triple bond N. So there are many reasons that affects on IR band. The first reason is conjugation. Pi-resonance conjugation lowers the energy of a double or triple bond. The effect of this is really observed in the IR spectrum. So if you see this example, and you can see the carbonyl group is attached directly to the aromatic ring. So there are here resonance structures, and you can see that the carbonyl group absorb as a lower wave number 1684, while the carbonyl group far away the benzene ring, there is no resonance, so it absorbs at the normal range around 1750. The conjugation will lower the observed IR band for a carbonyl from 20 to 40, provided the conjugation gives stronger resonance contributor. Also, if we have a different X like NH2, CH3, Cl, NO2, we have different absorbance. We have a different wave number actually. If we have NH2, the carbonyl group absorb at 1677. We have methyl absorb around 1687. If we have a chloride, it's absorbed around 1692. If we have a nitro group, it's absorbed around 1700. Due to what is the reason for this? The inductive effects are usually small unless coupled with a resonance contributor. Discuss about show the difference between methyl group and chloride above. The second reason is steric effects, usually not important in IR spectroscopy unless they reduce the strength of bond, usually pi bond, by interfering the proper orbital overlap. We have two different examples. Here's a methyl group as a structure at the right causes the carbonyl group to be slightly out of plane. interfering with resonance, while in the second example, no effect. The third reason is strain effect, changing the bonding energy force by the constraint of the ring will cause a slight change, hybridization, and therefore bond strength. Different ring size, so we have a different wave number for carbonyl group, as you can see in this slide. As a bonding angle decreases, carbon becomes more electronegative as well as less sp2 hybridized. Bonding angle lower than 120. The last reason is hydrogen bonding. Hydrogen bonding causes a broadening in the band due to the creation of continuum of bond energy associated with it. In the solution phase, these effects are really apparent. In the gas phase, where these effects disappear or in lieu of steric effects, the band appears as sharp as other IR bands. Gas phase spectrum, 1-butanol, as you can see in the right side, and steric hindrance to hydrogen bonding in adenine tertiary butyl phenols. There is a steric hindrance here, okay? A hydrogen bond can interact with other functioning group to lower frequency, as you can see in this example. Here we have OH and hydrogen atom interact with oxygen of carbonyl group by hydrogen bonding. So carbonyl have a wave number, carbonyl group has a wave number actually 1701. Thank you for this is a last slide of my discussions, and I'm happy to discuss many subjects. Actually, maybe in the second videos I will discuss NMR spectroscopy, mass spectroscopy, and please subscribe the channel and for more videos and support this channels for more videos. If you have any comments, please write your comments and I will reply. Thank you for your attentions.